Hello everyone, welcome to lecture 11 of the online course on modern display technologies, flat panel displays. Today's lecture we will be covering the fundamentals of liquid crystal physics. So, in this lecture and the next lecture we will try to cover all the fundamentals. So, here is the lecture outline. We will first look into the brief introduction to liquid crystals. We will talk about the liquid crystal phases like rod like, which is calamitic liquid crystals, and disc like, which is also called discotic liquid crystals. Then we will briefly discuss the thermodynamics and statistical physics relevant to this topic. So, we will brush up couple of important topics in thermodynamics like entropy, thermal equilibrium, thermodynamic laws in closed system, Boltzmann distribution, thermodynamic quantities, and some criteria for thermodynamic equilibrium. So, we will not go into too much of details of this, but a bit of basics is required for you to understand how liquid crystals work. So, with that let us go into liquid crystals. So, when we talk about liquid crystals, they are basically mesophases. That means, it is a phase of matter that exists between a crystalline solid and a isotropic liquid. So, somewhere in between liquid crystal lies. So, what are the molecular shapes? So, primarily they are composed of non-spherical organic molecules. So, you can see two types of molecules shown here. So, these are basically the chemical structures. Okay. The first one is for the calamitic liquid crystal, this one is for the discotic liquid crystal, and these are basically the space filling model. So, this is how typically they will look like. And if you think of a physical model for calamitic, you can assume it like a elongated rod like molecule, and for discotic it is basically a flat disc like molecule. So, what are the dimensions? The dimensions of these molecules are typically a few nanometers in size. Okay. So, the typical length will be around 2 nanometer and the diameter is around 0.5 nanometer. So, the aspect ratio, which is basically the length to diameter ratio for the case of rods, and if you think of discs, it is basically the diameter to the thickness ratio. So, typically it is greater than 5 in the case of liquid crystals. Now, due to their non-spherical shape, so these molecules can basically exhibit both positional as well as orientational ordering. Now, what is the requirement for liquid crystallinity? So, the first important thing is the balancing act. That means, the molecule must contain both the rigid core and a flexible tail. So, what is the role of this rigid core? The rigid core basically favors the orientational and the positional ordering, and the flexible tails that basically disfavors ordering. So, it basically maintains the fluidity. And how to determine the phase? So, when it is too flexible, you will see that no orientational order basically takes place, and when it is on the other extreme, that is too rigid. So, there a direct transition from isotropic liquid to crystalline solid. That means, the intermediate step of liquid crystal is basically skipped in this case. So, what is important is a balance between these two ordering and disordering, so that you can get a stable formation of liquid crystal mesophase, that is a state of matter which is in between crystalline solid and isotropic liquids. So, if you put a vision towards the molecular structure of the calamitic liquid crystal, you can see the representative molecule here is basically a 4' N pentyl 4 cyanobiphenyl. So, you can use a short form like 5CB in this case. So, if you look into the structural component, you see a rigid core, that is basically this biphenyl group. So, this provides the structural stability, and then you have this flexible tail, which is a hydrocarbon chain that introduces fluidity. So, typically as we have seen, people use a cylinder for approximating this one. So, despite there is some asymmetry, okay, you can closely model this using a cylinder to make the physical model for this kind of molecules. So, it allows rapid rotation, that means you have rotation which is in the order of nanosecond, okay, around the long axis, okay, and that averages out the molecular irregularities. And the other thing is that you have dipole symmetry. So, here you can see that this 5 Cb, okay, has a permanent dipole moment because of this Cn head group that you see here. Okay. So, the molecules basically have equal probability of pointing up or pointing down. So, that basically results into a symmetric phase, and the distance between the two carbon atoms is typically 1.5 angstrom, and that basically gives you the molecule a overall length of around 2 nanometer and the diameter is around 0.5 nanometer. So, that is how the physical model is obtained, and a cylinder makes a good approximation to this particular shape. Now, we move on to the other type of liquid crystal molecules, which is the discotic liquid crystals. So, the structure here is composed of a rigid core with multiple flexible tails that you can see here, which are basically like the branches extending outwards. So, these branches typically lie in a single plane. So, that is how you can actually do a physical model of this structure using a disc, and there is no permanent dipole moment which is perpendicular to the plane. You can also use another model called a bowl model when there is a permanent dipole moment that exists perpendicular to the plane. So, you can actually do two kind of modeling, disc model or bowl model, depending on whether that is the permanent dipole moment or not, that is existing perpendicular to the plane. So, if you have a bowl model, this basically breaks the reflection symmetry and it can lead to spontaneous polarization if the dipoles align along the same direction. So, what is the molecular dynamics here? The rapid rotation basically occurs around the central axis, which is perpendicular to this molecular plane, allowing the molecule to behave like a symmetrical disc or bowl in case of physical interactions. And what is the role of these flexible tails or branches? So, these are basically essential for preventing the formation of fully crystalline solid, because they inhibit the strict positional ordering that is required in case of crystalline solids or crystals. So, let us look into the liquid crystal phases. The transition between the phases is primarily driven by temperature. So, that allows you to move from high energy disordered to low energy ordered states. So, here is how it looks like for calamitic liquid crystals. So, this is a schematic representation of the different phases in the case of rod-like molecules. So, here you see you have a crystal or a crystalline solid, then you have a bit of disordering with increasing temperature, that is called smectic C. Okay. So, the next phase is called smectic A. We will go into the details. So, you can just see how the liquid crystals change, and in nematic you also see. So, here there are distinct orientation of the planes. So, that basically tells you about the positional ordering, and this is the orientational order that you can see column wise. Okay. So, here you can see that that is the positional ordering is more or less disordered here, but the orientational ordering remains, and then you have isotropic liquid where both positional and orientational ordering is not there. The next one is for the discotic liquid crystals. So, here you can see crystalline solids, they are pretty much in positional as well as orientational ordering. Okay. So, with increase in temperature, the positional and orientational ordering slightly gets disturbed. With nematic it is further, and here it is in every direction. So, it behaves like a isotropic fluid. So, absolutely no positional and directional ordering. Okay. So, these two schematic representations basically tells you how the phases change in a liquid crystal, if it is a calamitic type of liquid crystal and if it is a dyskotic type of liquid crystal. Now, let us go into the details of the rod like or calamitic liquid crystals. So, we will start with the low temperature one, that is the crystalline solid. So, here you can understand that we see full positional and orientational ordering of the crystals here, of the liquid crystals. So, the molecules are basically fixed in the lattice, okay, and the diffusion almost stops. Only thing you can see here is that they are slightly tilted, and that is their orientation. The translational viscosity becomes infinitely high. So, nothing drifts or moves. Okay. Now, you go to the other cases, the schematic A. So, here basically the molecules arrange into layers, okay, and you can clearly see the difference between these two, that here the director, that is the n cap or the normal, is basically perpendicular to the layers. So, this basically behaves like a 1D crystal. Okay. So, you have got ordered among the layer normals, okay, but a 2D liquid within the layers. So, here they behave like a 1D crystal, but inside this they behave like a 2D liquid. Now, if you look into the schematic C, which is the intermediate state between this crystal solid and schematic A, you will see that here the features are similar to schematic A, other than that the director, that is n cap, okay, is basically tilted relative to the layer normal. So, the layer normal is basically along this direction, that is Z, okay, but the n cap is slightly tilted. So, this basically represents significantly higher viscosity again, but the polydomain schematic material basically behave like grease. So, there is some viscosity and movement. Next is the nematic phase, which is the simplest liquid crystal phase. So, here if you carefully observe, you can see that the orientational ordering is present, but there is absolutely no positional ordering, okay. And the director, that is the n cap, which basically is a unit vector that represents the average direction of the molecular long axis, okay, that is more or less there, okay. Whereas, the molecules are kind of, they swivel due to thermal motion. However, if you take a time averaged direction, you will see that that is more or less uniform macroscopically. So, what are the characteristics of nematic liquid crystal? The molecules diffuse freely and the viscosity remains low. So, in the case of uniaxial nematics, you will see that the short axis of the molecules remain disordered, but there is kind of orientation in the long axis. Next, we move to the isotropic liquid that happens in high temperature, where the ordering is no longer present. So, there is absolutely no positional and orientational order. The molecules can move freely, just like materials flow in water, okay, or just like water molecules. Okay. So, here the translational viscosity becomes comparable to water, and you can clearly see that the molecular axis point in different directions. So, it is, that is why called isotropic. Now, coming to the phases of the disc like or dyskotic liquid crystals, the first one, as I mentioned already, that happens in low temperature is the crystalline solid phase, where positional order basically develops along the columns. So, you can actually see formation of a full 3D crystal lattice. Now, in the columnar phase, you see the molecules are getting stacked in columns, but within the columns the positional ordering is not there. So, orientational ordering can be seen, but the positional ordering is not there. Okay. So, between the columns it is arranged periodically in a 2D plane, just like a 2D crystal. Next we move to the nematic phase here. This is the discotic nematic phase. So, this also possesses orientational order. If you take the average of the directors, that is n cap coming out of this plane of each of the discs, but you see there is no positional ordering, right. And when I say the directors n cap, it is basically defined as the average direction of this short axis, which is basically perpendicular to the disc plane. So, as a result of two properties along the short axis and long axis, they basically exhibit birefringence, that is two different refractive index along two different direction, and this is because of the different polarizabilities between the disc plane and the short axis. The last one here is the isotropic liquid. So, it happens again in the high temperature case where there is no positional and orientational order. So, the liquid crystal basically behaves like a standard liquid. So, with that, now we will have a brief look into some of the basic concepts in thermodynamics and statistical physics, because that will be allowing you to have some idea about how this phase change happens in liquid crystals. So, why this matters for liquid crystals, this thermodynamics and statistical physics? We will see that the phase transitions are basically driven by competition between energetic preference for order and entropic preference for disorder. Okay. So, the equilibrium is decided by extremizing entropy or minimizing the appropriate free energy depending on the constants. So, what are the important quantities here? The first one is entropy. So, for a macroscopic system, entropy basically measures the number of accessible quantum states. So, sigma can be given as ln of g, where g is the number of accessible quantum states. So, typically it is g is very large number, around 10 to the power 23. Then other important quantity is the fundamental temperature tau. So, energy small u flows from high temperature system to low temperature system until a equilibrium is reached. So, you can say 1 over tau equals dou sigma by dou u, okay, at NV. N is basically the total number of available quantum states, and V is basically the volume of the system. And the third important quantities are the conventional temperature and conventional entropy, capital T and capital S. So, these basically connect the macroscopic state counting to macroscopic thermodynamics. So, you can see capital T equals this fundamental temperature divided by Kb, which is the Boltzmann's constant. Similarly, capital S, which is the conventional entropy, is nothing but sigma, this entropy, times the Boltzmann's constant. Okay. So, Boltzmann's constant Kb, I believe all of you know, it is 1.381 into 10 to the minus 23 joule per Kelvin, right. Now, let us discuss the entropy and thermal equilibrium. The first important concept is the multiplicity of states. So, if you consider a state that is composed of two subsystems 1 and 2, the total number of accessible quantum states G will be basically the product of the individual states, or you can write G equals G1 G2. Okay. Now, next is important feature is additivity of the entropy. The entropy is basically defined as the natural log of the total number of accessible quantum states. Okay. So, this makes entropy an additive quantity, because if you write sigma equals ln g and if you replace g equals G1 G2, so you can write this as ln G1 plus ln G2, which is nothing but sigma 1 plus sigma 2. That means, you get the additivity of the entropy, where the main system will have an entropy equal to the sum of the two subsystems entropy. Next is energy dependence. So, you can see the entropy is a function of the system's internal energy small u. So, sigma is basically sigma a function of small u. So, with that let us look into the thermodynamic laws in closed system. So, there are two important laws to remember. The first law is the conservation of energy. So, the energy is conserved in a closed system. So, if two subsystems are in thermal contact, the total energy small u remains constant. That means, you can write small u equals small u1 plus small u2, that will remain constant. That means, delta u1 plus delta u2 will be 0. So, any change here, a positive change will lead to a negative change here, so that you maintain that constant. The second law is of maximum entropy. Okay. So, it says the equilibrium state of a closed system has maximum entropy. So, it tells you that a closed system will naturally evolve toward a state of equilibrium that basically maximizes total entropy. So, you have delta sigma, which is delta sigma 1 plus delta sigma 2, that will be greater than equal to 0. So, with that let us understand the Boltzmann's distribution. So, if you consider a system at constant temperature that does not stay in only one energy state. So, higher energy states are basically exponentially less probable. That means, the lower energy states are more likely to happen than the higher energy states. The probability of a state basically depends exponentially on its energy, and the partition function that basically collects contributions from all possible states. And once you know this partition function, average energy and other properties can be calculated. We will see this in the subsequent slides, do not worry. So, this idea is very important for molecular orientation in liquid crystal, and that is why we are studying this. So, let us take some examples here. So, for a system that has got capital N states, where the energies are defined as epsilon 1, epsilon 2 up to epsilon n. So, there you can actually say that the probability for the system to be in the energy state epsilon I is basically P of epsilon I. That can be given as e to the power minus I epsilon I divided by kBt divided by the sum of all these probabilities to be in all the states. So, you do summation over I to capital N e to the power I epsilon I divided by kBt. So, what is the partition function? So, the partition function is defined as Z, which is basically the sum of this. So, this is basically the partition function. Okay. So, you can write this as your 1 over Z into this term, right, as simple as that. So, the internal energy or the average energy of the system can be given by capital U, which is basically the average of this energy. Okay. So, that can be computed over as sigma epsilon I P of epsilon I. So, here the denominator can be taken out as 1 over Z, that is the partition function, and remaining you left with epsilon I times this numerator, which is coming here. Okay. So, if you use this equation 2, you can write dou Z by dou T. Okay. So, if you do the first derivative, you get this one. Okay. So, you can basically simplify this term and write u equals kb t square by z dou Z by dou T, and once you put this thing here, you get kb t square dou ln Z by dou T. Okay. It is very simple maths, you can just do the calculation in a notebook and verify those equations. So, other important parameters are the extensive versus intensive quantities. So, when you say extensive quantities, that basically depend on the size or the amount of the system, something like internal energy U, entropy S, volume capital V. Intensive quantities are basically independent of the system size, something like the temperature capital T and pressure capital V. So, the internal energy changes due to heat absorbed. So, the internal energy of the system changes due to heat absorbed and work done on a particular system. So, the change in the internal energy capital U of the system is basically the sum of the heat absorbed, that is basically dq, and the work done, the mechanical work done to the system, that is d capital W. So, you can write this equation d capital U equals d capital Q plus d capital W. Okay. So, the pressure volume work, okay, is one common form of the mechanical work. So, the mechanical work, that means when a system changes the volume, that is dV under external pressure capital P. So, you can say that the work done is basically d capital W, which is minus P dV. Okay. Now, here you see the negative sign basically indicates that the work done by the system during expansion, that means your volume is increasing. So, you have a dV greater than 0. Okay. That decreases its internal energy. Now, if you consider constant volume, that is dV equals 0, in that case if no mechanical work is performed, so that is why the volume change is not there, and you will see that the change in the internal energy is simply equal to the amount of the heat absorbed. So, d capital U becomes only dq. So, how do you define the temperature? Based on the thermodynamic definition of the temperature, that is 1 over capital T equals dou capital S over dou U. So, the heat absorbed during a reversible process can be related to the change in the entropy, that is d capital S. So, you can write dq, that is TdS. So, if you consider the general case where you consider a variable volume, there you can combine the heat and the work together, and the fundamental relationship in thermodynamics for internal energy becomes like this, where you have d capital U, that is TdS minus PdV. Okay. So, here we will look into some more thermodynamic quantities and useful free energies. The first one is the enthalpy H, that is basically the heat absorbed at constant pressure. So, for a system, the enthalpy H is basically defined by the heat absorbed at a constant pressure. So, Helmholtz free energy F or A is basically, okay, we will come to that. So, pressure, okay. So, enthalpy H can be defined as H equals P plus UV, and if you try to write in the differential form, this is dH equals TdS plus V dP. So, at a constant pressure, that means dP is 0. So, you have the change in enthalpy to be simply equal to TdS, that is equal to the heat absorbed. Next, we will look into Helmholtz free energy. So, this is represented as F or A. This is basically a thermodynamic potential that measures the useful work obtainable from a closed system at a constant temperature T and volume V. Okay. So, it is basically defined as F equals U minus Ts, where U is basically the internal energy, T is the temperature, and S is the entropy, right. So, it basically represents the portion of internal energy not lost to the disorder. Okay. So, it is often called the work function as well. So, you can write this in the differential form as well. So, you can write this as dF equals, so du can be written as minus S dt, and this can be written as minus P dV. So, if you consider a constant temperature system, that means your dt is 0. In that case, the change in Helmholtz free energy is simply equal to minus P dV, that is the amount of mechanical work done to the system. So, if you take the derivatives of this one, you can also find S equals minus dou F by dou T when V is constant, okay, and you can also find P equals minus dou F by dou V when T is constant. Okay. So, next we move on to another important parameter which is called Gibbs free energy. So, this is the thermodynamic potential that measures the maximum reversible work a system can perform at constant temperature T and constant pressure P. So, it basically determines reaction spontaneity. So, a decrease that is a minus delta G will indicate a spontaneous process, and an increase that is a plus delta G indicates a non-spontaneous process. So, you can write this Gibbs free energy G equals U minus T s plus P v, or you can simply put it as, because U plus P v is basically H. So, you can write G equals H minus T s. So, in the differential form it looks like d dou, or you can say dg equals minus s dt plus v dp. Fine. So, this is particularly useful for processes occurring at constant temperature and pressure, which is more common in chemical reactions and phase transitions. So, how do you relate Helmholtz free energy to the partition function? So, the connection between microscopic states and macroscopic thermodynamics is basically bridged by the partition function capital Z. So, using the relation F equals U minus T s and the statistical definition of the internal energy, the Helmholtz free energy can be expressed in this particular form, that is F minus T dou F by dot T at V equals kB T square dou ln Z over dot T. So, you are basically using the equation 2a and 3, okay, 2a and there is equation 3 there somewhere. Okay. So, in this case the left side of the equation can be rewritten using the quotient rule. So, you change the left side, right side you leave it like this, and then integrating this will yield a direct bridge between this Z and the free energy, that is F. So, finally, you get F equals minus kB capital T ln capital Z. So, Z is basically the sum over all the states, because we have seen how Z looks like. Z equals sigma I equals 1 to n e to the power minus I epsilon I over kBT. Okay. Thus, you can say that for a system at constant temperature, the entropy can be calculated based on the probability rho I of the system that is being in state I. So, you can write it as S equals minus kB and then ln of rho. So, this can be written as, so this is the average of this value. So, it can be written as minus kB sigma I rho I and ln rho I. Yeah. So, what is the criteria for thermodynamic equilibrium? If a closed system changes from a non-equilibrium state to the equilibrium state, the entropy basically increases, or in a different way you can say that the entropy increases until equilibrium is reached for a closed system. That means, you want dou capital S to be greater than or equal to 0. But under practical laboratory constraints, it is more convenient to use the free energy minimization principle. Okay. So, that is easier. So, here are the different constraints and the equilibrium criteria, and these are the associated physical meaning. So, when you have a closed system, you maximize the entropy, that means your delta capital S will be greater than or equal to 0. The physical meaning is that there is no energy exchange with surroundings. When you have a constraint like constant T and V, the equilibrium criteria is to minimize the Helmholtz free energy F, that means delta F should be less than or equal to 0. So, that is the best descriptor for fixed temperature and volume. If you have constant temperature and pressure, in that case you obtain equilibrium by minimizing the Gibbs free energy G, that means you want dou G less than or equal to 0. So, that is the best descriptor for fixed temperature and pressure kind of scenarios. And if you have constant temperature and pressure with electric work, in that case you basically minimize G minus WE, that is the electric work. That means you basically obtain equilibrium by obtaining this delta G minus WE, this will be subscript, okay. It is not V W, subscript T less than equal to 0. So, this is important when an external source does electrical work on the system. So, I hope this gives you a brief overview of our recap, because you might have studied thermodynamics in your BTech curriculum. So, a bit brief review and recap about that thermodynamics and some ideas about the liquid crystal. So, with that we conclude this lecture. If you have got any doubt regarding this, you can always drop an email to this email address mentioning the course name on the subject line. Thank you.